This is our last video on ultrasound, and we're going to be looking at how ultrasound can be used to determine non-destructively if there's a problem with material, or to determine the size of a baby's head. We're also going to look at how we can use something called the Doppler effect to measure the speed that an object is moving away using, again, a sound wave or radar. Okay, so using ultrasound is going to be the title of this section. And again, we can find information on this on pages 108 in the textbook if you'd like to have a look there. So last time on the first video, we looked at a graph which looked something along these lines, where we had amplitude and time, and we sent out an initial pulse, and we received a pulse back. And we were looking at an object that might have looked something like this. So let's picture a block, and this time, rather than trying to find a wall in the distance, we're going to see if we can measure how thick the block is. So we're going to put our transducer up against the wall of that block. We might use a coupling agent, coupling gel like we did on the last one, or we might in some way clamp this transducer to the block, which is something we couldn't do obviously with the pregnant mother. And we're going to send those sound waves travelling through our block like this. Again, they're going to propagate through, reflect off the back wall, and there's our detected pulse, our echo. So we could measure that time difference between there and there, and knowing the speed of sound in steel, we could work out that distance. Alternatively, if we know the distance there and we know that time, then we could use this method to work out the speed of sound within steel. And it's just a simple speed equals distance over time, not forgetting that the distance is there and back. So remember to divide your answer at the end by 2. I want to think though, what happens if this occurs? What does that show us if we pick up an extra couple of pulses in the centre? Well, what it tells me is that somewhere inside this material there's a change in density, and it may well be that there's a crack. And the time between those two pulses can tell me how large that crack is. Time between these two pulses tells me how far in from this side the crack is, and the time between these two pulses tells me how big this distance here is. So it allows me to do a test on this material in a non-destructive manner, which is really important. It means I don't have to cut it open to sample it, and what I'm getting is a reflection off every single boundary. So I'm getting a reflection off here, I'm going to get a reflection off here, I'm going to get a reflection off here. So I've got my 3 pulses there, my 3 echoes that are being returned. Okay, and that might be useful in the context of maybe looking at an aeroplane's wing, or maybe looking through some steel piping, that kind of thing, a girder to check whether there is a crack or not inside that material. We can do the same thing when we looked at this pregnant lady last time. So it might also give us a similar reading if we looked at a pregnant woman and we looked at that baby again, and we could use the echoes that are coming from the baby's head on one side and the baby's head on the other side, and again that might give us some different pulse echoes coming from those different sides of the baby's head in order to measure the size of the baby's head that's within the mother. And that's really useful because then you can compare it against other babies. And particularly we might be looking for this sort of length where you're looking from what's called the crown to the rump length, and that length is really quite good because it gives you an indication of its growth rate. You might also look at its femur length here in its leg and just check that everything's growing properly. So they're the main uses. The second part of this video is about this thing called the Doppler effect. Now you should be familiar with this, certainly from GCSE, where you'd have heard about the idea of redshift. So redshift, if you remember, is to do with galaxies and how they're moving away. But I think an interesting or an easy way to understand what's going on is to think about when an ambulance goes past, and if you haven't heard it, then listen for one next time as it goes past our ears. So I'm going to stand with my ear in there, and as my ambulance goes past, the ambulance is going to be emitting a constant wavelength of sound, a constant frequency, constant wavelength of sound. However, my ambulance is moving relative to me. So as it's moving towards me, from the ambulance's point of view, it's giving out sound at a set frequency like this. As it moves towards me though, it's compressing those sound waves. So my ear detects those sound waves as being far more bunched together than they actually are. Which means that lambda decreases as it's moving towards me. As it passes my ear, you'll be familiar with that idea, because you'll hear this nina, 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 that sort of noise. As it goes past us, that sound wave will then become stretched, okay, slightly longer than it was before. So if it's moving away, lambda increases. That shift between those two lambdas, actually, in fact, the shift between that lambda and our moving away lambda, gives us something called the Doppler shift. Okay, and the Doppler shift is simply the difference between the two wavelengths. The larger that shift is, the faster the object is moving relative to us. For example, if we were stationary, then we've got that sort of wavelength. If we're moving away slowly, then it's going to become slightly spread out. If we're moving away quickly, then we're going to get something like this happening with our longitudinal waves. And we could draw those in transverse form as well. So if it's stationary, it might be looking like that. If it was moving away slowly, then it might be looking like that. If it's moving away really quickly, then we might get quite a long stretching of our wave. Now that's over exaggerated. Almost certainly you'll have come across that idea with red shift when you did Unit 7 perhaps at GCSE, certainly in Unit 1 in fact at GCSE, and what you'll have looked at is some things called emission spectra. And at one end down here you'd have had red, and at the other end down here you'd have had the blue end of the spectrum. And what you'd have found at GCSE is that there are certain parts of the spectrum which certain gases or certain elements gave out more than others, and that's to do with their electron levels. So for example, sodium, we'll use the yellow pen for sodium because it does give off a very yellowy orange light. Sodium is going to have two really strong bands of light being given off in here in the yellowy orange sort of region. Now those bands, if the sodium was moving away from us very quickly, are going to be shifted towards the red end. Their wavelength is going to be longer and they'll be shifted this way. Now notice they don't become red. It's unlikely that your eye is going to be able to tell the difference between, but the wavelength has got ever so slightly longer. So they may have shifted from something along the lines of let's say around 620 nanometers, and they might now become 622 nanometers. Okay, even then that's probably an over-exaggeration. It would mean it's moving away very quickly. Now for you don't actually have to work out how fast it's going, you just have to be able to tell the examiner that if it's got a longer wavelength then it means it's moving away. If it's got an increase in size then it means it's moving away faster. So if it's 624 nanometers, you'd be able to tell me that the one at 624 was moving twice as fast away from us as this one here at 622. Now that can be applied to radio astronomy, so looking out at our stars. It can be applied using those little radar guns that the police have, and it can also be applied, and I think this is a rather brilliant way of using it, to look at red blood cells within our body. Now imagine we've got an artery here, maybe inside this little baby, and we want to look at the blood flow within that artery, again non-destructively, so without cutting into it in any way, shape or form. We want to check that blood is flowing in one direction only. In other words, for biologists, that our valve is only letting, whoops, wrong way round, is only letting blood through in that direction, and that valve is doing its job and stopping the blood coming back in the opposite direction. So what we do is we take our ultrasound emitter from outside the body, so maybe the surface of the body is out here. We take our transducer, we put it up against the body, and we send sound waves in to the body like this. Now they can be continuous in this case, rather than pulsed, and we get those sound waves returned, and the transducer is going to detect any change in wavelength that compared to its original wavelength that it sent out. If that wavelength's got longer, it means the blood flow is moving away in this direction, and the more it's got longer, that allows us to determine whether it's moving quickly or not. And we might use that sort of thing with a continuous wave in the transducer to look at aortas in a baby. We might look at the 4 chambers in the heart and check those 4 chambers have developed correctly, and you should be able to see then that you get some areas of red, some areas of blue shifting as well going on, which is the opposite way, whereby if it's moving towards us the wavelength gets shorter, so it moves this way, and that tells us the blood is moving the opposite direction, which is right inside a heart, because you should have some areas with the ventricles and some areas with the atria where blood flow is going to be moving in opposite directions. Okay, so that's the uses of ultrasound. Make sure you understand all that, replay the video if you haven't got it all, and make your own notes on it.